Hello everyone, welcome to the today's session. So in this session we will study about the combined loading and their formulas. So up till now we have studied about the principal stresses, how to determine the principal stresses and how to determine the planes on which the principal stresses are acting. Also we have studied the maximum shear stresses and the plane on which the shear stresses are acting. So, and also the normal stresses, shear stresses, that also we have studied in the previous video lectures. So in this lecture we will study about the combined loading, means two different type of the stresses if it is acting on a member. So if it is acting onto the member, at that time what will be the effect or what will be the effect onto the stresses. It may be principal stresses, and also we determine the principal plane on which the stresses are acting if the loadings are combined, means two different stresses or two different loads are acting onto the members. So let us start with this slide first. So combined loading means basically we are taking the two types of the loading. First type of the loading, or we can say it is a bending or bending moment is there, it is acting onto the member. On this particular slide you can see there is a shaft is there, circular shaft, and there is a bending moment is acting on one of the axis, and also along with this bending moment there is a torsional moment is also acting, means that there is a torsion. So already we know that torsion is a twisting moment due to the applied torque. So that is a torsion moment and the bending moment. So these are the two different loadings are acting combinedly onto the member. That's why this particular member, it is in the combined type of the loading. So let us consider a circular shaft. So in the figure you can see the circular shaft is there, subjected to bending moment is also acting on one of the axis, and there is a torsion, means symbolically it is represented by capital T for torsion and bending moment for capital M. So both these loads are acting on the different axes. So let capital M is the bending moment, capital T is the torsional moment, and capital D it is assumed as a diameter of the shaft. So as we have studied in the unit torsion, there is a torsional formula we have studied. So from that formula if you can use this formula to finding out the shear stress also. So shear stress due to torque T, so we have the torsional formula, this tau is divided by R is equal to T upon J. So we can determine the tau by taking this TR divided by J. So this R value is nothing but the R is the radius of the shaft. So radius means half of the diameter. So D by 2 you can put, and also J, this J value is the polar moment of inertia for a solid circular shaft. So that value is also we know that pi by 32 d raised to 4, right? So if you put these values, so after simplification you will get the tau value 16t divided by pi d cube. So this is a shear stress due to applied torque. We will have this relation after using this torsional formula, so for a solid circular shaft. After that, bending stress. So this is all about that shear stress due to torque and bending stress due to bending moment, because of most of the time there is a, we know that whenever there is a applied torque is applied or twisting moment is applied, so there is a maximum shear stress is occur at the surface at the maximum radius. So that's why this shear stress is occur due to the applied torque. And second, that bending stress due to bending moment. So maximum bending stress is occur due to because of the bending moment also it is acting into the shaft. So we can determine the bending stress due to bending moment. We have this relation, this bending flexural formula already we know that we have studied in the unit number 3, bending stresses. So we can take the help of this formula and we will try to solve this bending stress from the bending moment. So m upon I is equal to sigma upon y. So now sigma is equal to m y. So y is the distance of the centroid from the extreme fiber. So that y, because of the shaft is circular, so this y is nothing but that half of the diameter, so from the centroid to the outermost fiber or extreme fiber. So this d by 2 value is there of y, and I is nothing but the moment of inertia, pi by 62 into d raised to 4. So that you can put into this, and after solving this you will get that relation 32 m divided by pi d cube. Okay, so this sigma means the bending stress value, the relation we are getting 32 m divided by pi d cube. Okay, so normal stress is sigma x or sigma y for the solid circular shafts are also there. So this bending stress we have determined. Suppose the stress is bending stress which is acting in the x direction, it is sigma x. If it is acting in the y direction, it is taken as a sigma y. So this sigma value we can take on which axis we have to determine the stress. So you can take that value sigma x or sigma y. So this relation 32 m divided by pi d cube. So these are the important formulas. You need to remember these formulas because based on these formulas some problems are asked for the combined loadings also. So first, that maximum shear stress, minimum shear stress, or major principal stress or minor principal stress. This basically, if it is the stress which is acting or bending stress which is acting in the one direction only, at that time you can use this formula. So as you already knows that if it is the stresses or bending stresses are acting in both the direction, so formula it is a little bit changed. So right now this formula is only for the stress which is acting in a one direction, either x direction or y direction. You can take this sigma by 2 plus or minus sigma by 2 bracket square plus tau square, right? So this is the formula of principal stress. If for one value you have to take the plus here, and for other value, that is a sigma p2, that is a principal stress, so you can take this minus sign. Okay, if it is your value it is coming positive, you can take it as a tensile stress, and if it is a negative means nature of that stress is compressive. So after that, the principal planes, so you know that this principal plane tan of 2 theta 1 is equal to tau twice of tau xy. So this again this relation we already used in the previous slides or previous video lectures also. So this tan 2 theta is equal to 2 twice of tau divided by sigma. So it is already proven by the derivation also, this it is equal to T, that is a torsional moment, divided by bending moment. So you can use this formula also, because as we know that the circular shaft which is acting, that two different loading, one is the torsional moment is also acting, and also there is a bending moment is also acting onto the shaft on either ends. So principal planes, if you are determining theta 1, so we know that there are two principal planes which is acting mutually perpendicular to each other. That's why the second principal plane we can determine by theta 1 plus 90 degree. And maximum shear stress, so as usual that maximum shear stress can be determined by using this sigma p1 minus sigma p2 divided by 2. So either you can determine maximum shear stress by using this, or this particular, again second formula is also there, but these formulas are only for the single stress in a one direction. That's why there is only sigma is taken. If it is that bending stress are acting in the both the, or we can say the direct stresses are acting in both the directions, either x direction or y direction, at that time you can take both the stresses, sigma x as well as sigma y also. So right now this formula is only for the sigma in a one direction. That's why it is only taken sigma. Instead of sigma x, you can directly take as a sigma. So sigma by 2 divided by bracket raised to square plus tau square. So from that also you can determine the tau max. So I hope these formulas are also helpful for you for the coming solving the different problems. So I hope you remember this, and this is the topic of combined loading. means many of the times the bending moment is also acting and the torsion is also acting for a member. In that case, you can use these formulas for the solving of the various types of the problems. And also you can see this equivalent bending moment and the torsional moment. So these formulas, the derivation is available in the books also. So but right now this formula you just see that let m suffix e is the equivalent bending moment which produce some normal stress alone, and capital T suffix e means equivalent torque due to combined effect of bending moment and torque. Okay, so this formula it is coming right now directly, formula it is written, but there is a derivation is also there. If you require the derivation, you can go through the derivation also, but right now you remember the formula. This m suffix e is equal to 1/2 capital M plus under root of m square plus t square. So also we can write this another way, me is equal to 1/2 m plus or minus t suffix e. So what is the Te? Te is the equivalent torque. So the value of equivalent torque is m square plus t square whole under root, right? So this Te is the equivalent torque. So normal stress due to axial force, if you have to determine the normal stress due to axial force at that time, this simple basic relation you can use, that sigma bending stress is equal to axial force divided by cross section area. So cross section area, suppose that circular bar or circular solid shaft is there, that time I by 4d square. So very simple, this normal stress can be determined for due to axial force, this 4p divided by pi d raised to 4, right? So I hope you understood and you try to remember these formulas, because some coming problems are depends on these formulas. If you remember the formula, you can easily solve the problems also, and these derivations are also available in the books also. So if you want, you can go through the derivation also, so how this formula it is derived. Okay, but from the examination point of view, these formulas are important. So I hope you understood. Thank you very much.